we already explained how to justify the position of your premixed friend and to understand when they move through the flow region closer to the stagnation point. For this example, stagnation point, then you will see they will induce the larger flow stretch. Okay. Now we try to give you the idea because we will give you some experiment results to tell you how the flow stretch influence the friend extension limit. Okay. Now we need to give you some background on our opposed jet flow with rotation. I hope you remember in our previous the paper published in International Journal of Human Transfer, we already introduced the flow structure for the non-rotational flow, right? But in that paper, we describe the rotating behavior get involved with the rotation of your flow jet. Okay, since the upper burner and the lower burner can be rotated with the regular rotation speed. Okay. How to think about the flow structure influenced by the flow rotation? This is a typical explanation from these illustrations. Okay, from A, B, C. A tell you if you do not have a strong rotations, the flow structure actually they still maybe you can see this is around with irrotational flow. The flow structure basically described by our co-flow study nicely, right? Now, when you have some flow rotation, you remember has in maybe in your daily life, well, okay, sometimes you want to drink a tea, right? And you put some tea leaf into your water, and those tea leaf will stay in the bottom of your cup. Now you use the spoon to rotate it, and you will figure out those tea leaf will be concentrated at the center portion because the flow motion. Okay, now you can think about when you do the rotation of your flow, you can look at the upper flow or lower flow either. If you look at the flow pattern change in the lower flow, you can find out when you increase the rotation of your injection flow, that means initially without rotation, all the flow, basically they are flow and follow the actual position, actual direction, right? That means the actual momentum is the mainly of the flow momentum. But when you do the rotations, it means that they have a circumferential centrifugal force. Then this centrifugal force will point outward. Most centrifugal force will push the radial momentum. Initially is weak, but they will become stronger by the influence of the centrifugal force in the flow region near the exit plane. That means the radial momentums increase in this region. Now the axial momentum will reduce, become weaker, and also they do not have enough radial momentum to going out near the stagnation plane. With increasing the rotation speed as much as possible, they will reduce the frame strength in the stagnation plane. In this sense, they do not contain enough flow momentum to flowing out. Additionally, they suck in the outer flow into your flow region. Here, you can see they will produce some flow moving into your stagnation plane regions. Then they produce a recirculation zone. They just have a just like a meter, okay, because there is a complete symmetric flow pattern exists near the stagnation plane. But when you do the experiment more, because those kinds of flows suck from outside with a strong fluctuation, those kinds of fluctuation will induce the so-called turbulence. Later on, you will figure out there is some turbulence, small turbulent AD will exist in the original stagnation plane regions, and they are separated with the flow pattern outside of this circulation zone. Here we still can have a very nice laminar flow pattern, but inside of the flow, then they will small AD to let you there is already a turbulent flow. those flow structure I will be described in the paper we published in Combustion Science and Technology. I will give you this paper and upload it. You can download it to see some flow structures you can observe. Okay, but I just try to explain it, and you can see the flow pattern variation from this. This is a segmented diagram, but I want to show you additionally from the velocity measurement. Okay, here I just want to tell you how the flow structure vary with the rotation speeds and based on the description on radial velocity profile. Okay, we started from here without flow rotations. That means the rotation speed is equal to 0. You can see here, this is the radial velocity profile for a given. I think this is the position at the radial distance equal to 14 millimeter. Okay, here this is the radial velocity distribution for non-rotating flow. But when you make a rotation, you increase your RPS, the rotation speed, from 4 continuous to 6 to 8 to 10. You can figure out, as I mentioned, when you increase the radial the rotation speed, actually you increase the radial momentum near the flow region near the exit plane. Okay, caused by the centrifugal force in the vicinity of your of the flow near the exit plane. Now this this radial velocity be large in this region, but since we convert some of the axial momentum to radial momentum, then they will reduce the originally they should move out through the extension plane. The radial momentum is reduced, and you can see here the radial velocity in the lower flow region increased, but for the upper flow regions they were reduced. Okay. This kinds of reverse variation on radial velocity will be enhanced as you increase the omega. Okay, 6, 8, and then 10. You can see radial velocity is continuous increase with increasing omega in the lower flow region, but in the upper region closer to the original stagnation plane, the radial velocity is reduced by increasing the rotating speed. Okay, and here there is the shadow region, means we cannot do the measurement because these regions the velocity fluctuation is too strong. Actually, that means that we already suck in certain amount of the flow from the outer region, outside boundary, outside surroundings, and they start to initiate some fluctuation. And we don't, we do not do the some averaging or do the data analysis in these regions, but they just show you a strong data fluctuation. Then we start to do the average and at this point, but they just tell you in these shadow regions, they show you the turbulence characteristics, and this boundary, actually this boundary is a continuous extent from the small boundary, the more extend to the flow region near the exit plane. Okay, this is a typical flow structure variation shown by radial velocity by increasing the flow rotation. Okay, now you can figure out if you have a frame exists here, definitely you will see they will experience the flow stretch initially. For example, here we assume the frame exists here. Initially, without rotation, the frame speed is large, right? This is a larger radial velocity. That means that they have experienced a larger frame stretch, but the radial velocity is reduced. That means the frame stretch is reduced with increasing omega. Okay, in this sense, they tell you the flow rotation gives you a positive influence on the variation of frame surface because it can reduce the frame stretch. Okay. Now we look at more precisely from our paper. You just read through it in the International Journal and Smart Transport. Okay. Here you can see This is for the actual velocity, and this is for the radial velocity. I'm sorry, I need to mention again here. This is the actual velocity because the symbol is not the same for different paper publication. But anyway, you need to know this is for actual velocity distribution variation, but this is for radial. Okay, then you can see here the first one for given this is the actual velocity. Actual velocity. This is a non-dimension equal to 1. And in this case, we control your concentration are the same by changing your rotating speed in the variation of rotating speed experiments. That means the frame speed actually is fixed. Okay. Now, originally, without rotations, the position sit here at first position. But when you rotate means that now the actual velocity change reduce here, right? Now the position will move to the upstream side from 1 to 2 to 3 by changing your omega from 0, 4, and 6 RPM. With increasing the rotating speed, the frame will sit closer to the exit plane of your burner. Now the idea is I mentioned when your friends shift to the position near the stagnation plane, they will experience larger frame stretch, right? But this is a conversely tell you when this frame will shift its positions to the upstream region closer to the exit plane of burner, then they will experience a small flow stretch. Okay, now you understand those kinds of variation from the flow field variation. Now we can see the experimental results from the other paper. I want to tell you the results. Okay, go back to our lecture notes and let's look at the page 112 at first. Okay, here they say how the rotation motion change the flame stage and then improve the combustion intensity. And this is a system we use and we already described before without mentioning the rotation. But now we add the DC motors to our burners to make this upper and lower burner be rotated. Okay, and here this is a typical experimental result we have. We have a double frame as I mentioned. Okay, here there is the upper frame and there is a lower frame, and we have a suction. Therefore, there is a double frame bank in the outer regions. Very nice double frame that we make it rotate. Now let's look at the results. For example, I give you this one. This is this is for the mixing frames, okay, and horizontal axis represent the extinction concentration. As you remember, we are doing the experiment for frame extinction, and horizontal axis represent how much the rotation we will have, and expressed by the rotation radius per second, okay. And those experiments is under different kinds of injection velocity. Let's look at the first part. Okay, if you consider non-rotating flow, that means you as I described earlier, if you at this point and we try to exempt the frame extension for different injection velocity. For example, for the first one, number one experiment this time. This is the number one experiment, and the injection velocity is high, and the second is lower. We continuously decrease the injection velocity, then you will find out the extinction limit starting from the 5.6, then 5.30 something, 5.35 maybe, and very close later, the next one very close to 5.2, and the final one is equal to 5 points. That means that when you were given premixed frames, you do the experiments actually for higher flow speeds. Okay, then you will extinction in a larger mixing concentration. That means that it is easier to be extinction. Okay, when the flow velocity reduced up to the 19.6, for example, this is 5, then this flame can be survived even under the 5% limit we may have from the literature report. Actually, 5% limit limit is just a reference because of so many kinds of experiments. You cannot exclude all the influence coming from the surrounding. Now, just looking at the reactivity of your premixture, therefore, 5% is not absolutely barrier justified for chemical reactivity. Okay, but as a reference only. So in this experiment, you can see even for very small flow velocity, flow field, 19.6 injection velocity, then you can have a flame survive very closer to the 4.9%, something 4.98% or something here. Okay, but anyway, this is the first point I want to mention. Without flow rotations, and you can see there's by vary the injection velocity. Actually, you change the flame stretch. Okay, larger injection velocity will give you larger radial velocity on the premixed flame. If you have a small injection velocity, the radial momentum convert from the axial momentum will be reduced, then they will have a smaller radial velocity acting on the flame. Then this flame can survive to the lower concentration. And this is one factor I want to mention. Now the second, we try to introduce the flow rotation into your flame. So I choose one of the experimental results. For example, for 5.6, starting from the omega equal to 0, that means the experimental first set. Okay, the injection velocity is around 61.5 centimeter per second. As you remember, I just explained, originally your flame may sit in a certain positions in your opposed jet flow. Now you try to increase your flow rotation. As you remember, now due to the influence coming from the centrifugal force, actually the radial momentum is increased in the flow near the exit plant. Then they will reduce the axial momentum in the flow near the stagnation plane. Actually, the flame will shift closer to the exit plane in this moment. Okay, I already explained from the cold flow variation. When they shift a position closer to the exit plane of your burner, that means that they will experience a small flow stretch. Then they can survive. Okay, to the lower extinction limit. The 5.6 will be reduced to the maybe some point, maybe 5.5, as you increase omega equal to 8 continuously up to 21st, they can reduce as much as possible, even very close to the 5 point, right? For each line, they show the same characteristic. Okay. Later on, I don't want to expand too much because this will something get involved. But you can read through the reason why they move to the minima, then they will go up. Actually, this is caused by the other fact. As you remember, when you increase the flow rotations as much as possible, they will induce some flow from the outer region, and those kinds of induced flow will bring some fluctuation. Those kinds of turbulent fluctuation strong enough, they will extinction the flame easily. Then this again they start to increase. This is caused by those kinds of influence from the outer sucking fluctuation. Okay, but this figure tells you by using different kinds of mechanism, you can try to reduce the flame stretch on the flame. And this is basically this is evidence to tell you by the flow rotations, the flow stretch is reduced. Then extinction limit can be reduced. Extinction limit reduced means your flame can survive under a lower the mixing ratio. Okay, this is a typical example that you to understand how the flame stretch influence affect the burning intensity or premixed flame in terms of flame speed or flame position. Now we go back to the other examples. That means the the flames under compression. Okay, this is our Bunsen flame. You may think about there is two different kinds of Bunsen flame. One is a circular cone. As you remember, if you have a uniform velocity profile injection, then you can have a perfect circular cone. And there is the angle. Okay, there is a alpha angle. Actually, they are corresponding to the angle on the top. And here there is another one. You may have a circular parabolic shape. Usually, when you have those kinds of flame shape, that means that the flow velocities on the X-plane is not uniform, and it depends on how kinds of flow management in your tube you will have. Maybe as I give you the several examples, usually we have a perfect circular cone, right? And sometimes you will have some curvature occurs on the base of your premixed flame, and when your flame move to the outer region of potential cone, it's easier to have this circular parabolic shape. But anyway, you can see, look at your flame surface, and because we are looking at the change of flame surface, right? For the Bunsen flame, we are looking at the flame surface vary with your coordinates. Then when you move your coordinates systems, in this case, we put the origin on the tip of your on your Bunsen flame. But you can think about that we start from the exit plane. Okay, we start from the exit plane. You move from this position to the flame tip. You can see the circumferential flame shape continuously reduce to a very minimal small boring on the top of your cone flame. And those kinds of variation can be described based on analytical formulation. I don't want to describe it, but I just give you the results. For the Bunsen flames, they give you the formula for estimate the Coleridge number by this way. Okay, but if you submit the flow condition into your equations, then you will reduce a simple relation for the Coleridge number that tell you the non-dimensional Coleridge number is equal to minus here. This is minus. You remember originally we say the dA divided by dt. That means it's a stretch. Stretch means the value Coleridge number is positive. Okay, but in this case, since the flame is under compression, then the Coleridge number will be a negative value. Okay, this is a minus sign here. LH, the pre-Tinton thickness divided by the adiabatic flame speeds, and this is for non-dimensional. And by submitting the flow velocity function into this bracket, then you will reduce the W. W means the actual velocity of your given flow. Sin, there is the 2 alpha mixing. Okay, can you put it into 2 alpha? Alpha is the angle we always describe. And there is the important the quantity here. There is a 2 RF. RF is the position, the radial position of your flame. Okay, for example, here for this one, the RF is this big, is large. When you move your position along the actual directions, then the RF will continuously reduce. Okay. Okay, this is a result, the formula for circular cone with a sharp apex. Okay, that means that has the perfect cone shape. And you can figure out as alpha reduced. What is the meaning of alpha reduced? Alpha reduced means you are moving along with along the flame surface and in the actual directions. In the actual directions, you will see RF is continually reduced. When you have a smaller RF, that means that you have a larger Coleridge number. Okay, that means the strength of compression or the strength of negative stretch becomes stronger and stronger. Okay, now you will figure out at the tip of the burner or of the Bunsen flames. Usually the flame the French surface will shift to maybe very close to a single point. This is not possible, but there's a small region. So usually you can see for many Bunsen premixed flame, the tip is very bright. Very bright means there is a strong energy intensity near that region. Okay, but this is not always true. I will tell you what is the next point, because now we just tell you the influence coming from the flow convection. Okay, but be remember from the beginning when we're dealing with the transport phenomena, we always give you the idea when you're dealing with flow characteristics. Usually they always have a so-called back flow motion. That means that we look at your flow structure basically from the microscope point of view, but you should remember they still have very important consideration on molecular level. That means you need to look at the microscope diffusion process. Now we are focusing on the d over dt. As you remember, d over dt, we tell this is a material derivative described by flow mechanics, fluid mechanics. And fluid mechanics, actually, they give you this idea based on the microscope point of view. Okay, we are talking about the time variation, coordinate variation, and the local flow velocity. Those are corresponding to large-scale observation. Actually, that is a microscope point of view. Now, as I described, those kinds of French stretch, actually they may not occur because of the influence coming of the diffusion process. Now, the next step, we need to get involved with the Lewis number effect. That means we need to think about the balance of mass diffusion and the thermal diffusion or heat diffusion in the heating zone. I will describe it. When you have a flow stretch that represents flow convection, and then the other one is Lewis number represent the diffusion strength. We couple it together, then you will find out there is a very interesting burning characteristic on premixed flame.